Hello everyone, welcome to third tutorial video on Ansys Mechanical. In this video, we are going to talk on different type of force loading condition in finite element analysis. So the talk is actually going to be focused irrespective of any software tool. So the same boundary conditions or same type of loading can be applied in any of the simulation tool. Only thing is that the way that they might be applying will be little different uh, from the things that we are going to discuss next. So to start with, if we look at any of the finite element tool, so they usually start with a CAD model, and once that the CAD geometry representation of your actual problem is available, after that we discretize those CAD model is different element types. Now, yeah, in finite element method, there are different type of elements using which we can represent the CAD structure. In some ways, there are some simplified elements that are also available. Like if you look at a very thin type of CAD model, like if you are modeling a very thin sheet, then we can use directly the cell element. So similarly, if we have a very slender structure, like we can represent those things as using the beam element. So here you can see there are different, these are almost this type of element you will see in most of the finite element softwares. Now, if we talk on the practical perspective, like whenever we are trying to model anything, it means that we are doing nothing but trying to replicate the problem that we are facing either in academics or industry through the simulation, through this computational environment in order to predict some type of response that might get generated into the system after the application of the load. Now, if we look at the loading types, so there are different type of loadings that are usually is applied in reality. Like you can see, this is some broader characterization has been done. Like first is your force characteristic. So the loading can be your normal load, shear load, bending load, torsional load. If the loading is something that is of distributed nature, so this is something that we are talking as a point load. But suppose if the loading is distributed, then it can be distributed over the surface, it can be distributed over the any edge inside your model. Similarly, the loading can be concentrated. It means that it is, whenever we are saying concentrated load, it doesn't mean that it is going to be applied in at a single location, because in reality there is nothing like area tends to zero. So what mathematically it means that this is actually applied in a very small area. So we are calling it as a concentrated load. Similarly, the volumetric load is there. So for example, if you are trying to apply some type of acceleration loading, or if you want to apply some type of gravity loading to the model, then those things will come under the volumetric loading. So this was the distribution and the force characteristic. But every loading is means has some time dependence nature associated with it. So now if we look, first is your static load. So what a static load actually means is that your loading is something that is applied in a very not very, but it's getting applied in a time frame of seconds, so that it is not going to induce any type of inertia into your structure. Now the next is sustained load. So sustained load is like, suppose I am applying some type of load, and after some time, after a fixed amount of time interval, I'm keeping the load as a constant for hours. So if we are putting it a load constant in terms of the hours, it means that there might be some type of creep behavior that will come into the picture. So usually for concrete application, RC beam application, we go with the sustained loading type of thing in order to predict that the component is going to fail due to the creep or not. Similarly, in even the sustained load cannot be only of the structural nature. Suppose if you are keeping a body subjected to a temperature, high value of the temperature for a long duration, again the material degradation will happen over time. So those things can come under the sustained loading condition. Next is your impact loading. So this is something that if your loading is time dependent and also very fast, so that will come under the impact loading condition. Next is the cyclic loading. So cyclic loading is something that in the here you can see in this image. So if it is something that is of repetitive nature and also following a sinusoidal wave type of pattern, then that will come as a cyclic loading. Even the other type of pattern can also become can be modeled as a cyclic loading condition. Only thing is that it should have a definite period with a repetitive nature. Now, this is something that we discussed individually, but if we look at any of the practical application, what actually happens is that there is not a the model is not going to be subjected to a single loading condition. There can be multiple loading situations that will means there can be that component might be subjected to multiple loading scenarios at the same time. So, as we were discussing that usually the industrial application is not subjected to a single type of loading condition. Just to emphasize on the fact, let's take an example of O-ring a simulation example. So usually if we look at this thing, so that is a detail of the CAD model. I'm just taking this example from a blog. So this is a very good blog, and in case if you are trying to model an application similar to this, you can go through this read up, that is O-ring seal joint. So here if we see, like usually if we are going to put any seal in the assembly state, so that is automatically going to be subjected to some type of pre-stress type of condition. So that pre-stress type of condition is like usually on the periphery of this reel, there will be some type of normal force that is already applied. On top of that, because this is seal is this problem is something that is designed to avoid any type of fuel leakage. So if any fluid is present inside the system, that fluid is again going to cause some type of pressure loading over this seal that is present here. So it means that there are two type of loading. One is due to the pre-stress, another is that this the fluid pressure will also be there. So this is just one example. But if you look at any of the industrial applications, so usually they will I have seen in cases where it is usually a combination of 4 to 5 type of loading condition over uh, an assembly. Or you can go through this one. So this is you can see how this simulation proceeds. So this is in the fitted state. After that, it will also be subjected to some type of fluid pressure. Now let's start. So what I did will do is that I will show you how you can apply all the different type of loading conditions. We will not go into much detail, but I will try to cover as much as possible with the different settings that are exposed in Ansys Mechanical for modeling this different type of loading condition. So for this, I have taken a very simple example. So I already prepared the CAD geometry. So I'm not going to go to a space claim and create this geometry for the demonstration purpose. I will directly start with the from the Ansys Mechanical modeling environment. So let's start the discussion. So once you open the model inside the mechanical, so on top you can see that there are different options using which we can control the selection, that is either based upon your geometrical entity selection. So any 3D like or any model that you are importing inside the mechanical will be composed of vertex, edge, faces, and volume. So you can see it's bottom to top designation. So first will be your vertex, that is like a point. So if you go to the selection, you can let me just here you can see you can select the vertex. If you want to select the edge, you can first either use the smart selection. So that is a new feature in the recent versions. So that will automatically select based upon the geometrical entity which is closer to your cursor. Now the next thing is that if you want to have a better control, you can change the selection to edge. Now once you click on the edge, it will only select the edges inside the model. It will not select the faces. If you want to select the faces, you can go and click on the faces, then it will select only the faces inside this model. Next is that you can also, like suppose in some cases, if you want to apply the loading directly over some node or on the elemental faces, you can go and select this mesh selection. So once you are going to click here, you can see automatically the view will change to the mesh, and now you can select individual mesh nodes to apply any further loading condition. Now let's start with the force characteristic. So currently I'm going to assume that whatever the load that I'm going to apply is something that is static in nature. So first is that normal load. So normal load you can directly apply by selecting the faces or selecting the edges or vertex in the model. So for example, let's take that this is a cantilever beam And what I'm trying to do is that I want to apply some type of normal force in the x direction. So as discussed, we can change it to the face. Then one way is that once you select the face, if you right click at the same location or in the anywhere in the GUI, based upon the selection, the available boundary condition will be exposed in the GUI. So suppose here I want to apply the force, I can click on the force. So automatically once we click on the force tab here, so you can see the selection is uh, assigned, like whatever the selection that was there in the GUI, that is automatically assigned here. Now next you will see there are different options, or I will say in a way that there are different ways in which we can define the magnitude of the force over this face. So first is that defined by vectors. So if you know that if you want to define the force in some specific direction based upon some geometrical selection, then you can use the vector view. So let's start with this vector. Let's give me a magnitude of 10. Now you can see by default it is assigning the force in x direction. But now suppose I want to change the direction of the force. So I want to apply some forces in this direction. So one way is that not in means one way is that you can directly, because this is something, the model is perfectly aligned with the global coordinate system. So you can directly change it to the vector, to the component view, and enter a value of 10. So this will change the direction of the forces. Similarly, you can give the x, y, and z components also. Now the next is that suppose if you want to use the vector view, so what we have to do is that we have to do some type of geometrical selection in the model to provide a direction for this force vector. So here you can see if I'm going to select this edge, okay, if I select this edge and hit on apply, so you can see the force direction is changing. Now if I'm going to select this edge, okay, this edge, now it will get aligned in a specific direction. We can also, like suppose if you want to define some forces in some inclined direction, like I want to define some force which is at 45 degree to this face. So for that what I can do is that I can go here, let me select these four nodes, and now you can see the forces are going to be aligned in this direction. So for defining this type of force directions, this vector component is very handy. Now the next is that if you want to apply some type of forces which are parallel to the faces, so for that again, one is that you can use the vector view and reorient the direction of this force. So if I'm going to use this vector view and change this force in this direction, so let me solve this model also, so that I will show you this how these forces are actually getting applied internally. So let me activate this nodal forces, because that will help us to visualize the force application at this faces. Now there is actually a command that means or user defined result that will help us to visualize the forces that were mathematically applied to this model. We can see this is how the nodal forces were present inside the model. So these are some reaction forces, so that's why the vector is oriented in the opposite direction. Now next is that suppose if you want to apply some type of bending load. So bending load is something that is applied on some type of rotational degree of freedom. Now whenever we are dealing with any 3D elements, we only have access to our translational degree of freedom, that is u, v, and w. We don't have any rotational degree of freedom in the model. So for that, applying any type of bending loaded or moments, you can directly use this moment condition. Suppose if I'm going to apply a moment on this face, let me delete this one. So I can give components, and suppose for this I want to apply some type of moment about z axis. So I can enter a value of 10 here. So if I'm going to enter a value of 10, it will apply a moment about Z axis. Similarly, if you want to reverse this direction, you can give a negative magnitude. So that will apply the moment in the reverse direction. Now the next is that, so using this moment, you will be able to apply the bending load and the torsional load. And again, the selection is something that you can apply at any, like any of this quantity, either on a vertex, edge, face, or even at some like node location. Now, yeah, I just wanted to highlight one more thing. Suppose if you want to apply any loading condition or the moment at some nodes, so by default, you will not be able to select the nodes directly inside this selection. Okay, now I think the recent version it is available. So another way is that what you can do is that if you are working in some prior versions, you can use the nodal force, nodal pressure, nodal displacement, boundary condition to apply any boundary condition, any of these things directly at the nodes. But only thing is that this will require you to provide some type of name selection. So for that, what you can do is that suppose I want to apply something at this set of nodes that are present over this face. I can right click here, create name selection. I will name it something like nodes underscore test. You can name it as per your convenience. And now if I will right click on this thing and create nodal name selection. So this nodal name selection I can directly select under this nodal force option. I apply here. So this will get applied. Only thing is for visualization, it is not something showing like this, but yeah, definitely it will get applied internally. Now next is that to apply the concentrated loads. So in finite element method, because we can directly access any of the nodes or vertex location, so we can apply any of the forces directly at the vertex locations that will act as a concentrated load. Suppose if I select this vertex, it means that the forces are going to get applied at this specific location. You can see this is getting applied only to this the node or the node that is present at this specific vertex. Now the another way is that you can also go to this mesh node, select here one node, and then you can change it to component and enter this value of 10. So this will again, based upon your even if in some cases it might happen that the location at which you want to apply this thing load is not a hard vertex. So in those cases you can directly use the nodal selection, that is the directly by selecting the nodes. Next is that if the load is actually distributed over some face, so in those cases you can use the pressure boundary condition. So if I'm going to use the pressure boundary condition, either I can select the elemental face or I can directly scope it to the face. Now if we look little in means if we talk it like how it is actually happening. So if suppose if you are selecting some geometrical face, so this geometrical face is actually composed of a set of your elemental face. So whichever elemental face that are going to be present under this which are mainly used to create this surface will automatically the pressure will automatically get applied to all of the faces. But in some cases we want to individually control the face location, so in those cases you can use the elemental face selection option. So suppose if I give the value of 10, you will see the pressure will get applied to this specific element. Now for applying any volumetric type of loading, if I right click here, I can see acceleration, standard of gravity, rotational velocity, and rotational acceleration. So these are something that is going to be distributed over the body. So whenever suppose if you are applying this acceleration, by default it is getting applied to all the bodies that are present inside the simulation environment. There are ways using which using the command snippet which can be used to control the bodies on which we only want to apply the acceleration load. But that is something that, yeah, means if you are interested, let me know in the comment section. Now, similarly, if you apply standard gravity, it is also applied to all the bodies. So we covered this force characteristic distribution. Now let's go to the time dependent. The time dependence first is a static load. So static load, you can apply this type of loading directly under the static system environment. Next is your sustained load. So sustained load, if you want to apply, what you can do is that, suppose I want to apply a sustained pressure load. So suppose if I select this face, you can see this time is something that is provided as an option to us. So even in static structural, it is something that we can call as a pseudo time. In transient analysis, it will be a real time. So suppose if I know that in 0 to 1 second, my amplitude is going till 10 MPa, and after that I want to keep the 10 MPa as a constant. So I can enter a value of 1 here, and I will put 0, 10 and 10. So you can see this is for the time duration of 1 to 10 seconds, the loading will remain constant. So this is how you can apply the sustained loading in the environment. Now the next is that, suppose if you want to apply any time dependent loading, then whenever we are trying to apply any time dependent loading, it means that we are planning to capture some type of inertial effect inside the model. So if the inertial effect is something that is of interest, we can add one another analysis system. So either you can add this analysis system at the workbench project level, or you can directly add from going in the home tab and then analysis system from this top ribbon. So suppose if I add a transient structure, and for a demonstration purpose, what I want to do is that I want to apply a force that is something like a stepped loading type of thing. So I will apply the load and then remove it. So let me fix this thing, and I'm going to apply the loading in 1 second. So let me 0.1. So you have to provide some type of initial, minimum and maximum time. So this will be used to decide the initial, minimum and the maximum time step from the solver's perspective. So I will put some link for this specific readup, and maybe in coming tutorials we will go into little bit more detail on the effects of the initial time step, minimum and maximum time step over the simulation. Now let me just do one thing. So we are using this one. So 0.5, I will apply 1 Newton and then bring back to 0. 0, 1, 0. So it's like a step loading I'm applying to this model, and this is getting applied in this specific direction. Or let me increase the magnitude. Now, while the model is solving, it's good practice to always keep a track of the force convergence. So as the model is simple, we can see this is a very smooth convergence pattern. Usually we don't get this type of pattern for a complex application. We will face the bisections and other issues, but this looks pretty beautiful. Now let me just plot the deformations. Now if I'm going to animate it, so just auto scale is there. Okay, but we can look at the vectors, and if I'm going to, so this is going to be the maximum location, and here it is coming back to its initial configuration. Let's see. Now the next or the final loading that is a cyclic loading. So suppose if you want to apply any type of cyclic loading, one way is that if you know the function, you can directly apply the forces or the pressure as a function. Instead of the magnitude, you can change it as a function. And let me just enter a function. So I will put once 100 into sine into 10 time, and if I change it to 100, and let's increase the time to 10 seconds. So now you can see. So either by using the function, so if you know the function, Only thing is that the function is something that is there are only few functions that are available, like sine, cos, tan, exponential, cosine inverse, tan inverse, power, log, and square root. So if you have any solve functions and other things, that cannot be directly used. So for that, what you can do is that you can do the extract this data, time versus force data in Excel, and then directly and use the tabular loading type of thing. Now the next thing is that in some cases what happens is that your loading is something that is also varying along the length. So for that, again, suppose I want my loading to vary from 10 megapascal to 100 megapascal along the x direction. So let me use the tabular thing. Okay, let me go here, and instead of magnitude I will use a tabular, and tabular dependent I can change it to the x-axis. Now if I'm going to change it as a x-axis, and I will create one coordinate system at this location. I will choose this coordinate system as a starting point. Then measure the length of this edge. So length is 168. So I will put a value of 10 here, and for 168 I will put a value of 100. Okay. So now I can see that the pressure is actually varying along this direction as a magnet from 10 to 100 MPa. Let me solve this again. And what I will do is that I will clear this result just to show you that how the magnitudes is varying along the space. I will select this face and let me plot this one. Now you can see the pressure is actually getting applied in a increasing fashion. So this is just to show you that this pressure load was getting applied. This is just this is not a pressure. This is pressure when pressure gets converted as a nodal forces. So this is a representation of that. So I think this is what actually I wanted to cover in this video. So let's meet in the next video. And in case if you like the video, don't forget to share it with your friend or colleagues. And please subscribe the channel. Thank you. See you in next video.